We're now going to introduce the concept of electric fields. We're going to start by considering a positive point charge in space. We know that like electrical charges repel and opposites attract, so it makes sense that if I were to place a positively charged particle in the vicinity, it would be propelled away. But what actually causes this behaviour? We understand this by defining what's called an electric field about our first charge, Q1. Nearer to the charge, the field will be stronger, as the lines are more dense, and conversely further away it will be weaker. It's our second charge, Q2's interaction with this electric field that caused it to move. Let's define this electric field using Gauss's law. Gauss's law states that the electric field over an enclosed area is equal to the charge enclosed divided by a constant, the permittivity of space. In our case, the enclosing area, termed the Gaussian surface, will take the shape of a sphere, and so the electric field at a point a distance r from a charge q1 equals q1 divided by 4 pi epsilon naught r squared. Now that we define the electric field, let's recap. Q1 produces an electric field all around it. At each point in the charge's vicinity, it has a direction and magnitude. If another charge, of the same polarity, is placed at a point in this field, it interacts with the field to create a force in the same direction as the electric field, with a magnitude related to its charge. We can write this as the force on the particle equaling E, the electric field, multiplied by the particle's charge. Note that this is the charge of Q2, not Q1. Now let's say we apply some force to our repelled particle from before so that it stays in place. We could now say that the particle has some sort of potential energy equal to the amount of work we just put in to get it there. Remembering that work is just force applied over a distance, and energy is just the capacity for something to do work. A simple test for whether or not something has potential energy is asking what would happen if it was released. If it moves, it had potential energy. As an analogy, consider an apple held above the ground. Some work is done to counteract the force of gravity, and this work is equal to the stored gravitational potential energy of the apple. The only difference is in our case, we're dealing with a repulsive electric force, not an attractive gravitational one. As work is just force acting over a distance, let's integrate our force equation to find a formula for the work. We're integrating over the distance we pushed this charge Q2, so from some point D1 to a point D2 near to charge Q1. The change in potential energy stored in Q2 is equal to the work done on Q2 to bring it from D1 to D2. Therefore, this is our formula for the electric potential energy difference between 2 points about a point source. If we divide through by the arbitrary charge Q2, we get a normalized expression for a change of potential energy simply termed the electric potential difference. This is also what's known as voltage. As a brief aside, instead of integrating our force equation between two arbitrary points, let's integrate from infinity up to a distance capital R from our charge Q1. The assumption we're making is that an infinite distance away from Q1, the electric field is zero. Therefore, what we are left with is the absolute voltage, that is, the potential difference from zero. As this is just a function of distance R from the charge, this forms another field, a scalar potential field in the charge's vicinity. Note that this does not have any direction, just magnitude. You can see also that all points equidistant from the charge producing the electric field have an equal potential, and these circles are called equipotential contours. We now understand how electric fields interact with charged particles to generate forces, and have developed from these forces an understanding of electrical potential energy and its normalized form, potential difference.